We continue then with Lorenzo Tesi from the University of Stuttgart. And he will actually present one of the so far main results from the Peter project. Okay, here he is. So Lorenzo, please.
Yeah. Okay, thank you, Rainer. So good morning, everyone. I will present here the talk about plasmonic metasurface resonators that we apply to enhance the Terahertz magnetic fields for high-frequency electron paramagnetic resonance spectroscopy. And this work is part of the Peter project. So I will start with a brief introduction, and then I will move to the design of these plasmonic metasurface resonators. And I will show a demonstration on high-frequency electron paramagnetic resonance measurement. Then, as you have seen in the yesterday, as a prerequisite for this future and emerging technology that we are trying to realize, we need to experimentally prove the plasmon enhancement of Terahertz magnetic fields in HFEPR experiment. And therefore, my work had two aims. The first is to demonstrate, to show experimentally this enhancement in the Terahertz. And this was done by using Terahertz transmission experiments and the high frequency HFEPR. And we took the opportunity to realize a new type of HFEPR resonator that works specifically for thin layered samples. I will show you briefly again what is electron paramagnetic resonance. So if you consider this radical molecule, which is temple, this has a spin 1/2, and in the moment in which we apply a magnetic field, we will have a splitting of the spin levels. If we send a radiation whose frequency matches the energy difference between these two spin levels, we will see an HFEPR signal. With HFEPR, we can determine the parameters of the spin Hamiltonian that describe the system we are investigating. In this case, for example, we just need the Zeeman splitting in term. And with this, we can determine the structural properties, the magnetic properties, and the environment of these molecules. And then the reason to go to high frequency HFEPR instead of conventional frequency is because we can achieve much higher resolution. Therefore, we have more detailed determination of these parameters. Then, as a unit for our plasmonic metasurface, we decided to use Diabolo shape antennas. This was the simulation of this was reported in 2011 from Grosjean. And how this works is if you apply an electric field to this antenna, you will have accumulation of electric charges at the opposite wings. Then you will have a current through the bridge, and around the bridge, you will have a magnetic field that is produced. Here in the simulation, you can see the concentration of magnetic field in the middle, so at the bridge position, and the electric field is instead accumulated at the corner. Of course, this was designed to work at 110 terahertz. What we aim is to go in the sub-terahertz, so 300 gigahertz. And therefore, we will have to simulate and, let's say, adjust this frequency resonance. It's also important to mention that in the moment in which you apply an electric field that is parallel to this antenna, you will have an activation of this antenna, so this effect. But if you rotate the polarization of the electric field of 90 degrees, the antenna will do nothing. And also this type of structure is suitable to integrate in a SPM unit, which is at the end what we need for our instrument. How this resonator should work. So in the moment in which, as you have seen previously, we send an electric beam, an electric radiation, we will produce a magnetic field, so this B1, which is absorbed together with the B1 we are sending, is absorbed by the molecule. And then because we will have a larger amplitude of this B1, we will also have a higher HFEPR signal, which can be that we go above the level of noise. So it determines if we see or we don't see the spectrum of our molecule. So this is the principle. And then we designed this resonator by numerical simulation in CST Microwave Studio software. Here I summarize the main parameters that we can optimize for the antenna. And by doing this, we were able to see a resonance at 275 gigahertz with a relative field enhancement, so the near field enhancement of almost 22. We also moved to an array. In this case, we took the same area of the antenna as before. So you can see the comparison with the single antenna, and you can see that the signal didn't improve. So the field enhancement didn't improve that much, but the signal is different, which means the antenna are interacting in some way. What really improved the enhancement is placing a gold mirror beyond the substrate. So in this case, you can see that the single antenna signal improves of a factor 5. So now we have around 100. And the array changed dramatically because now we have a very sharp enhancement with a high Q value. And the near field enhancement is now around 150. In the moment in which we use this gold mirror on the back, we have another parameter which is very important now, which is the substrate thickness, because you can see that by sweeping the thickness, we have a periodic behavior of this resonance, which is given by the Fabry-Perot effect that occurs into the substrate. And in our case, we are at this position of the signal. Also, we can sweep, we can change the antenna distance, and we can see that we have a plasmonic resonance only in this, for this value of the antenna gap. So from this, we can understand that the resonator we designed is quite complicated because we have the interplay of many effects that are occurring. We have the plasmonic effect of the single antenna, we have the Fabry-Perot coming from the substrate, and we have an array effect due to the interaction among the structures. We fabricated this Plasmonic Metasurface Resonator without the gold mirror, and we characterized by continuous wave Terahertz transmission. So here we have the setup, this is the source, the amplifier, the radiation goes through this path to the sample and then to the detector. And what we measure is these blue dots, and the blue line is instead the simulation. And you can see we have a very nice agreement overall. We also characterize the array with the gold mirror on the back in this double Terahertz transmission because we cannot apply a normal Terahertz transmission measurement. In this case, we use the high field EPR, high frequency EPR setup that we have. And again, what we measure is these blue dots, and the simulation is here the red line. And you can see that we have a match of the resonance of this resonator. We can also take a look to the electromagnetic field distribution. So for the final design of the resonator, this is the magnetic field and the electric field. The electric field, as you can see, accumulates at the wings, and the magnetic field is focused on the middle, on the center of the antenna. So this is the final design we fabricated. This is a 7x7 array of antennas, which have dimension around hundreds of micrometers. Then we moved to the high frequency PR experiment. We used as a sample temple diluted in a polymethyl metacrylate matrix and spin coated on top of the resonator. And this resulted in a thin film thickness of 330 nanometers. The instrument has been already shown by Dominic before, but I want to focus that we have 82 gigahertz and we can sweep up to 1.1 terahertz. And we can go up to 15 Tesla. And because we have such a wide range of frequency and field, we can think to record the field frequency map. So this is an example that was reported by Peter Neugebauer on manganese 12. And here you have the map of the frequency and magnetic field, and every line corresponds to a specific spin transition of the manganese 12. Then if you cut horizontally or vertically, you can go back to the traditional EPR spectrum in the magnetic field or in the frequency domain. And this is exactly what we have done also in our case with our sample. And we register this map, and you can see that all the signal we have lies on this diagonal line. This is in according with a Zeeman splitting term of a spin 1/2 that can be described by this formula. And if you look closely, we have peak at 287 gigahertz when the antenna are active. And this, if we cut the map along the diagonal, we can project then the results on as a function of frequency and magnetic field. And here, as a function of frequency, you can see we have this red line. So we have this peak, and the same measurement was repeated for the non-active orientation of the array and for a reference sample. And this reference sample is just a quartz substrate without any antenna, with the samples being coated on top. And you can see that we have a broad overall enhancement, but the main enhancement we have at the 287 gigahertz, so close to the what we have also simulated. And by comparing this red line with the reference sample, we see an enhancement of a factor 30. And now we should think about what we achieved. So this factor 30, we obtained it when we measure an entire sample. So the sample was covering entirely the substrate, which is much bigger. This is 3 × 3 millimeter substrate compared to the hotspot position of the antenna. And then we can calculate by numerical simulation, we can estimate how this increase would result if we place the molecules only on top of the antenna. And this we obtain a factor 7,500. Which means that if we start from the normal sensitivity we have, that is 10 to the power of 10 minimum detectable number of spins, with this resonator, we can go down to 10 to the power of 6 spins. And this means that we could increase the amount of sample, the possibility that of investigation of high frequency PR, and we can enlarge it to very thin layered sample and self-assembled monolayer sample, which is currently not possible. And with this, I finished. I want to thank all the people that are involved in this work, in particular Professor Vanslager and Dominic Bloss, and of course, all of you for your attention. Thank you very much.
Thank you very much, Lorenzo, for this talk. Are there questions? Yeah, Magnus?
Actually, I was just doing applause, but thank you for a very nice talk. I don't have any question at the moment. But,
okay.
Thank you.
maybe later.
Okay. Are there other questions?
Maybe I could have one then. So I was wondering a little bit on the different control experiments that you did when you have the let's say the cavity approach, having a spacer layer and the metal, which reminded me a little bit of our system. So did you try to do this with not having antennas at the top layer, by just a flat film instead, metal film, to only have the cavity effect? I know it's not so nice for your nanoscopy in the end, but just to understand what happens.
Actually not. I tried for one single antenna or for an array of antennas, but I never tried without any antenna. But that's a good point. I mean, I can definitely try.
Thanks.
Jakub?
Yeah. Hi, Lorenzo. Thanks for a nice talk. So my question is, do you have some prediction or some ideas how these antennas will change because you said that we will be able to measure these self-assembled monolayers. So how it would change the stacking, or these, because it's like object on the surface and then you will put something on it. So how it will change or can it change the properties of the molecules?
I mean, exactly. So that's really the point in investigating self-assembled monolayer. So the idea is that, for example, if you consider a normal molecular magnet, the properties of the bulk system doesn't need to be exactly the properties of the molecule after deposition on surface. And this is a really hot topic in the molecular magnetism community, to understand how these properties change when you place this molecule on a surface. And I believe high frequency PR can be a very important tool for this investigation, which so far was not, not really possible, because the sensitivity was always a problem. And so I hope we will see to solve your question with the time.
I mean, maybe I will like slightly modify it quickly. So I meant it more like that this antenna, it's like a structure on the surface, so it will change how it will stack, I guess, because it's like array of antennas, so it's like physical object on the surface. And then like how to imagine this monolayers. If you have, I don't know, CVD graphene on silicon dioxide wafer, it's let's say more or less flat, some defects, bilayers, and so on. But how this let's say structure of these antennas could change the, or it will be like separately on these antennas, you will sense it, or
yeah. So in that case, I have to admit, I don't know how this will behave. So yeah, I don't know, but maybe we can discuss it more in detail later.
Okay. No, thanks.
All right. Any more questions? No.
Yeah, actually. Thank you for this very nice talk. I was wondering, on the slide which you're showing here, you show that there's a strong increase from the resonant structures, a resonant increase of the field. And in addition, you see a broad background or a broad enhancement above 300 gigahertz. When you put a metal layer on the backside of your substrate, is this just a short which forces the B1 field to?
In this case, you mean?
Which just, yeah, exactly here at 300, between 300 and let's say 370, you have an enhancement. If you go to the right to higher frequencies, you have an enhancement. Where is this coming from?
We believe,
if you go down from your peak.
Here, you mean?
In the other direction here. You see this also in your experiments, I think. If you
this is another. It's as I show, it's a quite complicated resonance, because there are many effects that are occurring. So this is again coming from two main effects, which is a higher order of plasmonic effect of the antenna, and this is mixed with the Fabry-Perot. So also depends on the thickness of the substrate. So this peak is another. This broad peak is another convolution of this plasmonic effect with the Fabry-Perot of the substrate. I believe, but as I told you, it's we are still trying to identify every single effect and how they play together. So this is something that Martin Harton showed partially yesterday, and it's quite a complex problem, I would say, because they are overlapping each other, all these effects. So. But I believe this is a higher plasmonic coupled with a Fabry-Perot.
Thank you.
Yeah, thank you.